Hey guys, in this video we're going to look at question 8 from the practice final. We have the ring of polynomials with rational coefficients here, the ideal generated by x squared minus 2, and we have to prove that this quotient is a field. Okay, and what we need is some facts from class. First, that if K is a field, the ring of polynomials is a principal ideal domain. You need that fact. Then we need some facts about principal ideal domains, that if you have an irreducible element of a principal ideal domain, then that element generates a prime ideal, and in a PID, like that prime ideal also has to be maximal. Okay, and then for a maximal ideal, an ideal is maximal if and only if the quotient of the ring by that ideal is a field. Okay, so that's going to be our plan. We want to show that this is a field. We have to show that this polynomial x squared minus 2 is irreducible. Okay, solution. So our plan is to show that x squared minus 2 is irreducible. So let's write that down as like a claim or something. It's irreducible. Okay. So, I mean, this claim is essentially the fact that the square root of 2 is not rational, but let's go through all the details. Okay. So, first of all, we have a quadratic polynomial. If a quadratic polynomial is reducible, it means that it has a root. Okay. So, to prove our claim, we note that if x squared minus 2 is reducible, it actually factors as a linear times a linear, which implies it has a root. Then x squared minus, or is irreducible. I should mention that this is in the ring. We're working in the ring of rational polynomials with rational coefficients. If it is reducible, it has a root in the rationals. Okay, so now to show that this polynomial is irreducible, we have to show that it has no root in the rationals. Okay, this is something we know from, I think, what is it, math? Anyways, math from first year, But square root of 2 is not rational. If you don't remember, I'll remind you what happens, how you show it's not rational. I mean, in an exam situation, you would just say, but square root but we know square root of 2 is not rational. I don't expect you to go through this argument, but I'm just doing this in case maybe you forgot or something. Well, I'm going to remind you. So assume square root 2 is rational, and then write it in lowest terms. Something's wrong with this pen or something. Okay, so we write square root 2 with PQ coprime. In other words, having no common factors. Okay. And now, maybe, let me try. So we have that square root of 2 is P over Q. I'll just square both sides. Cross multiply, you have 2 q squared equals p squared. Okay, in other words, p squared is even. Or we could say that 2 divides p squared. Okay, but if p squared is even, p has to be even. So 2 divides p. In other words, you can write p equals 2r. And r is just another integer. Okay, now substitute p equals 2r into the original equation. You get 2q squared equals, now you have 2r squared, all squared, you have 4r squared. Oh, maybe I should be more careful. You know, you have p is really 2r, so 2r squared is, you know, quantity, or yeah. Anyways, okay, now a 2 cancels, and you get q squared equals 2r squared. And now q squared is even, so q is even. So right, in the same fashion, you can write q equals 2 times s, where s is an integer. Okay, now p is 2 times an integer, and q is 2 times an integer, so they have a common factor of 2, and that is a contradiction. Because we assumed that p over q is in lowest terms. So p over q was not in lowest terms. Okay. And that ends our proof that the square root of 2 is not rational. That proves that x squared minus 2 is irreducible. And then, now you can say, well, x squared minus 2 is irreducible, so this construction F is a ring modulo a maximal ideal, so it is a field. Since this x squared minus 2 is a maximal ideal. Okay, it's a field. Now I wanted you to write it in some like special way. Well, just notice like whether it's a field or not, like elements. So now let's finish off the question. Let the square root of 2 be the coset of x in this ring, which is in F, and notice that in this quotient f, which is a polynomials mod x squared minus 2, whenever you see x squared, you can replace it by 2. Okay, so now now you can see that every element of f can be written uniquely as a plus b square root 2, because whenever you see anything involving terms involving higher powers of x than x squared, you can replace any of the x squareds by 2's. Okay, so if you have an x to the 5th, well, that's really x times 2 times 2, and so on. Okay. Okay, so that's the end of that. And I guess what you can say is okay, so that's the end of that video. Thanks for watching.